As you may know, 3 points define a plane, and here we're going to find the equation of the plane through 3 points. They are 3, 0, -1, -2, -2, 3, and 7, 1, -4. Let's put together a brief visual here. How are we going to use 3 points to come up with the equation of a plane? Well, if we imagine a plane here, and let's label the points 3, 0, -1 will be P1, -2, -2, 3 will be P2, and 7, 1, -4 will be, what the heck, P3. And I'm just going to put 3 points on the plane here at random. I'm not trying to make them be in any particular place on the plane. I'm just using this for a visual aid. So P1, P2, and P3 are on the plane. Given any 2 points, I can form a vector between the 2 points. So let's consider a vector that goes from P1 to P2. We're going to call that the vector U. And then we'll look at another vector from P1 to P3. We're going to call that the vector V. If we form the cross product of U and V, then we will, by virtue of the cross product, get a vector that is orthogonal to both U and V. That vector will turn out to be the normal vector for the plane. And so the idea here is form 2 vectors, find their cross product, and then use any of the 3 points in the equation of a plane. In order to form a vector given points, we take the coordinates of the point at the head of the vector, subtract the coordinates of the point at the tail of the vector. In other words, coordinates of P2 minus coordinates of P1. And so we have -2 minus 3, -2 minus 0, and then 3 minus -1. Our vector U is then -5, -2, 4. Same thing for the vector V. We're going to use coordinates of P3 minus coordinates of P1. So V is going to be given by 7 minus 3, 1 minus 0, -4 plus 1. And so V becomes 4, 1, -3. Forming their cross product, U cross V. And it doesn't matter, folks, if we use U cross V or V cross U. But for the picture that I've drawn, I've actually given V cross U, because if we were to take the fingers of our right hand, point them in the direction of V, curl our fingers towards the direction of U, our thumb would be sticking up the way I've drawn N. So V cross U. What I was saying, though, was if we did U cross V, then we would simply end up with the vector that points down instead of up. It would still be a normal vector for our plane. V cross U, so our determinant is going to be the first row I, J, K. The second row are the components of V, so 4, 1, -3. And the third row are the components of U, and so -5, -2, 4. Go ahead and pause the video here and find this cross product. If you can take this all the way through to the end, come up with the equation of the plane, so much the better. For the cross product, we visually cover up row and column containing I, and we have 4 minus -2 times -3, so 4 minus 6I. Minus goes in front of the J component, 16 minus 15, plus -8 plus 5 for the K component. So V cross U turns out to be -2, -1, 3. I don't like all those negatives, and that's just a personal preference. So I'm going to use a normal vector 2, 1, 3 instead. I'm actually going to go with U cross V. Those components as my coefficients in my equation give me 2 times the quantity of x minus 3 plus 1 times the quantity of y minus 0 plus 3 times the quantity of z minus -1. And I'm using the point P1, which was 3, 0, -1. Simplifying that equation gives me 2x plus y plus 3z is equal to 3. That concludes the exercise, but I want to talk about a common thing that I see on exams, and it's this. Folks will sometimes try to form a cross product using the coordinates of the points that we are given. We cannot find the cross product of points. We can only find the cross product of vectors. We aren't always going to look at a visual, like a graph, for everything that we do, but we will in this case. I've used GeoGebra's 3D graphing tool. You can find a link in modules or on my website to plot the 3 points that we had: 3, 0, 1, -2, -2, 3, and 7, 1, -4. This is kind of small. And we can see that I've also given you the traces in the xy plane, just so you can see that, for instance, -2, -2, 3 is above the xy plane, 7, 1, -4 is below the xy plane. Also, notice that here the red axis is pointing to the right and the green axis is pointing kind of back. That red axis is the x-axis, the green axis is the y, and of course the blue one pointing straight up is z. That's our orientation here. Now what we did was we formed two vectors. One of them went from 3, 0, 1 to 2, -2, 3. The other went from 3, 0, 1 to 7, 1, -4. And we found their cross product. It's important to note that we found the cross product of two vectors. Now here's the thing. If I put 2 points instead of 2 vectors into a determinant for the cross product's not going to know the difference. But what you would be doing in that case would be, you'd be finding, say we use -2, -2, 3, and 3, 0, 1. Those are tips of vectors that do not exist in the plane. The tips do, but the vectors do not. And so you would actually be finding an orthogonal vector to 2 vectors that weren't in the plane at all. And so I just want us to be very careful about what it is that we're actually doing. Put another way, in order to make sure that the vectors that we're forming are actually in the plane, we have to subtract coordinates to get the vectors u and v before we use the cross product. Then when we found the cross product, we found a normal vector, and I did it again, I drew the wrong one. If we did v cross u, our normal vector would be pointing down. That was the normal vector for our plane, but the bottom line here is, folks, we can find the cross product of vectors, not of points. So please don't do that. People do it every term. Let's see if you can avoid it.